So we're going to cover falling objects up to examples 210 and 211. I'm going to save examples 212 through 215 for later because there's a lot of really good problem solving strategies in there that we're going to make sure we want to focus on in class. So falling objects. The first thing to consider when we talk about objects that are falling is that these are examples of uniform accelerated motion. So that means that objects are accelerating and they're doing so uniformly. And this alone tells us a little bit something about what these objects are actually doing. Right? That means that all falling objects are accelerating. So the best example of uniform accelerated objects actually happens to be Earth. And more specifically than Earth, objects that fall near the surface of Earth. You see here's Earth's surface, and here's an object that falls near the surface of the Earth is the best example of uniform accelerated motion. You've probably thought some bit and heard some bit about uniformly accelerating objects, and you probably have a general understanding based on your observations of what falling objects are. But there are a lot of misconceptions about objects falling near the surface of the Earth because in the pre-1500s, Aristotle had professed that objects that had different masses would fall differently according to their mass. And he actually said that two different objects, right, of two different sizes, right, would fall differently based on their sizes. The heavier object would fall faster than the lighter object. And that seemed to, nobody argued with it because that seemed to be true. They said, hey, when I see things falling, I do notice that heavier objects fall faster than the lighter objects. But that idea was kind of debunked by a dude, Galileo. And he was alive and experimenting from 1564 to 1642. There he is, handsome fella. So you see, Galileo, he said he thinks Aristotle is wrong. He says that objects, regardless of their mass, will fall at the same rate. And this was contrary to what a lot of people thought was true, and it might even be contrary to what you think is true. He says that they both fall with the same constant acceleration, which means that both of these guys are falling, and the acceleration that they're falling with, they start slow and they get faster and faster and faster and faster and faster, and that's equal to one another. Let's talk about how he did that. You see, a lot of people claim that Galileo actually performed a certain experiment. This right here is the Leaning Tower of Pisa. Alright, the tower is leaning, and it's really just leaning because the Earth sunk unevenly. But what Galileo did, people claim, is that he took objects and he climbed to the top of the Leaning Tower, right? And he had a whole bunch of people hang out down below. Hey Galileo, what you doing? I don't believe you. I think the elephant's gonna fall faster. Oh Galileo, you're so silly. Aristotle was right a long time ago. Well, Galileo took his two different sized objects and he released them at the same time and killed everybody below. No, really what happened was Galileo released two objects at the same time, and they both fell and hit the ground at the same time, regardless of the fact that they had different masses. Now, a lot of people say that this experiment actually happened, but it's not true. It was a thought experiment. And Galileo had a habit of making thought experiments, saying, hypothetically, if I were going to do this, what would the outcome be? And it's actually his method of thought experiment that helped progress science to this point, which is why, in some ways, he's called the father of modern science. He did not actually perform this experiment, but one experiment that he did perform had to do with ramps. So here he is. I'm on a ramp. And what he did was there he is. First, he made some evenly spaced bumps, evenly spaced tick marks. All right, imagine that the distance between each of those is an even spacing. All right, and then he allowed something from rest at the top of the ramp to roll down the ramp. And then, using his heart rate, because we didn't have stopwatches back then, he would compare the sound of the object going over each of the humps to the time that he was keeping track of with his heart. And so what he found was they made a sound like tick, 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 tick. Maybe something that you've heard. But what he found is that as an object fell, it took less time for it to cover the same amount of distance. So that means that as the object falls down, the time decreased. So as object fell, time to cover same distance decreased. And so then what he did do was he created a different type of spacing. He started the points closer and he got them further and further and further and further and further and further apart. And he tried the same experiment over again, and he spaced them out so that, in accordance with his heartbeat, because stopwatches didn't exist, every time as the object rolled down the hill, every time he did that, there was an even amount of time between them. So it would be tick, 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 tick. And from this, he actually derived the relationship between time and displacement. Right? So he came up with an actual, real mathematical relationship between the distance traveled and the time the object was in motion for all falling objects. And he did that by picking the slope steeper and steeper and steeper, and he was actually able to prove that this relationship, the distance, is actually proportional to the time squared. All right, so that means that every second squared gives you the change in distance. But the one thing that he did say, because remember he liked to simplify the science. So he said, in these situations, you must neglect air resistance. The reason that everybody thinks that the heavier object is going to fall faster is because of air resistance. And you've seen this. Because if you take a piece of paper and you drop it onto the ground, it doesn't fall the same rate as a rock. And that's because of air resistance. So he said that if you neglect air resistance, or you create a world where there is no air resistance, objects will fall with this relationship every single time. So we can summarize his big statement as this speech blurb right here. Right? At a given location on Earth, in the absence of air resistance, all objects fall with the same constant acceleration. Right? That's his major contribution to free fall motion and the study of motion. And we call that acceleration that all objects fall with acceleration due to gravity, and we give it the symbol g. And g, it just so happens, has a value that is known, measured, and confirmed, and that value is 9.80 meters per second squared at the surface of the Earth. Now I want to be a little bit specific about what I mean when I say at the surface of the Earth, and you'll also find this in your textbook. G actually varies a little bit according to the latitude and elevation. That means you go up in a mountain, G is going to be a little bit less. You go away from the center of the Earth latitudinally, and you're going to have a slightly different G value. So while gravity isn't 100% constant, exactly 9.800000 meters per second at the surface of the Earth, this value is consistent. In fact, when we think about it in terms of significant figures, right, those significant figures will take into account slight changes in elevation and changes in latitude. So we can ignore those slight variations for the purpose of free fall calculations. The one thing that I do want to say is that while air resistance, we can neglect it most of the time because objects will fall without obvious air resistance as long as you're not dropping a piece of paper or a feather. You can't ignore air resistance at high velocity. And in fact, the faster the velocity or the higher the velocity, the more of an effect air resistance will have. And so that's something, if you are the kind of person that in your textbook notes likes to make yourself little indicators for the future, I would maybe say in an air resistance little note like this. Make yourself that note and pull it out on a sticky tab and actually put it physically in your notes, so that when you come back to look at the effect of air resistance with increasing velocity, or you're looking for background information for a lab, hint, 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 that maybe that might be a good place to start. Okay, so those things being said, there's a few technical things that I would like to go over at this point in time. Alright, one of those technical things is that when we calculate free-falling objects, in the equations, instead of writing A, we write G. Right? Because on the surface of the Earth, G will always be 9.80 meters per second squared, so we might as well say, hey, in this frame of reference, we're on the surface of the Earth, so our acceleration is G. And also, because these things are happening vertically, instead of using x, we use y. So for example, for the equation x equals v naught t plus 1/2 at squared, right, that would be our traditional kinematic equation that we might use. If we're doing it for free fall, then we would change our x to a y and say y equals v naught t plus 1/2 gt squared, where the y is for our change in position in the vertical direction, and our g is the acceleration due to gravity. So that's a neat, convenient thing, and it's especially going to be helpful when we start doing projectile motions, which is soon. So again, if you're the kind of person that likes keeping track of notes for the future, you might want to say projectile motion help, and leave that indicator right there for talking about calculating objects in free fall. That might help you remember or keep things consistent to come. So let's take a look at an example. In example 210, it asks us, suppose that a ball is dropped from a tower 70 meters high. How far will the ball have fallen after 1 second, 2 seconds, and 3 seconds? So here's our situation. Here's our leaning pizza tower. And here's our pizza ball. And it gets dropped 70.0 meters. And so we want to know how far it will have fallen in those time intervals. Alright, and we're going to assume, of course, that t naught equals 0 seconds, so that in each of these, this is showing the elapsed time. Another thing that we need to assume every single time we do a problem like this is if an object is dropped, then we usually say that v naught is 0 meters per second. And the reason we say that is if it's dropped, you're not throwing it, you're not pushing it, you're not holding it back, you're just dropping it, you're letting it go, which means that when it was in your hand and the second that it left your hand, it wasn't moving. So now that we have those conventions, let's think about what we know. We can neglect air resistance because in this situation we're going to assume that the object is not falling fast enough for air resistance to be a big deal. So we say that acceleration equals gravity, which is 9.80 meters per second squared. And in this case we have a position, which we're going to say is a y value of 70.0 meters. Now, it's very important for us now to establish our axis. right now we have a ball and it's falling down. Right? One thing that I forgot to mention that I want to make sure that you know is that when we talk about gravity, we always talk about gravity as a vector. Gravity is a vector. All right, so we're just going to pause real quick, and I want to make sure that everybody knows is that gravity and the acceleration due to gravity is a vector quantity. All right, so that means that anytime we draw it, we draw a vector. And it's really convenient. Every time we draw that vector should point toward the center of the Earth. All right, it's always a vector toward the center of the Earth. So that means that if you're in space and you've got a mouse and he's orbiting space, right, that gravity vector that mouse is experiencing is toward the center of the Earth. And we'll get into this in a little bit, but this is what's responsible for orbiting objects. Likewise, if we switch our frame of reference to the surface of the Earth, and we bring our mouse back, that gravity will point toward the surface of the Earth, just like this, because toward the surface of the Earth is also toward the center of the Earth. So gravity is a vector, always points toward the center of Earth. It's really important that you remember that, so I wanted to make sure that we stopped and went over that specific piece of information. Now that we've established that gravity is a vector, that means it has to have a direction, and so does our position. Now this ball has been falling down, so we're going to set our position. We're going to set our y-axis. We're going to say that down equals positive. All right, so now our vector quantities which are our position and our acceleration due to gravity, and if we were going to calculate it, any of our velocities, all right, these vector quantities will have a positive or a negative. We said that y-axis down equals positive, so that means that it's going to be positive 70.0 meters because it's falling down 70 meters. And our gravity is going to be positive 9.80 meters per second. This is totally fine. Now let's say that you set your y-axis so that down was negative. That's totally fine. You can do that. You're in control here. Just remember that if you set your y-axis down equals negative, that your position, the distance, that displacement that you have, will be in the negative direction, downward, and your gravity will be in the negative direction, since down toward the center of the Earth would be negative on that axis. If you do that and you maintain your direction consistency, you will get the correct answers, just like here. So now we have our givens. We've established our frame of reference and we've established our axis. So we can, in this situation, we're going to use the equation y1 equals v naught t1 plus 1/2 gt1 squared. Now, this is an equation that you should be familiar with. It's x equals v naught t plus 1/2 at squared, but we've written it for the case of t1 equals 1 second. And we've written it for the case of an object who's falling with acceleration due to gravity, g, and moving in the free fall direction, y. So we can say that this will give us for t, give us the position for time 1.00 seconds. All right, for the time of 2.00 seconds, that position would be y2, and it would be v naught t plus 1/2 gt2 squared. And t equals 3.00 seconds. That would be y3 equals v naught t3 plus 1/2 gt3 squared. So now we have these three equations, and the only difference between them is how much time has elapsed. Remember, we said that the initial velocity is 0. Anything times a 0 is 0, so that means that for each of these equations, our v naught t turns into a 0 value, and we're going to have equals 1/2 gt1 squared equals 1/2 gt2 squared equals 1/2 gt3 squared. So we can plug in our values now. And when we plug in our values now, for 1 second, 2 second, and 3 second, we'll find our position 1, position 2, and position 3. Now, if you're looking and you said, I didn't realize that my time is what I was trying to find because I didn't realize I was trying to find my position because it gave me this displacement of 70 meters. Remember, that's just the height that we started with. So in this case, it's going to be 1/2 9.80 meters per second squared times 1.00 seconds squared. 1/2 9.80 meters per second squared times 2.00 seconds squared equals 1/2 9.80 meters per second squared times 3.00 seconds squared. When we solve these, our seconds cancel out, and we get, for time 1, we get 4.90 meters. For time 2, we get 19.6 meters, and for time 3, we get 44.1 meters, where the seconds squared inverse on in denominator for the acceleration cancels with the time squared in the numerator. And so that gives us the position, and we can see that, right, first it covers a small distance, and then it covers a much larger distance, and then it covers a much larger distance. And this makes sense when we compare it to the fact that the object is going faster and faster with each second that passes. So that being said, let's continue focusing on our example of an object on our pizza tower. Still a height of 70.0 meters. And we're going to consider time 1 equals 1.00 seconds and time 2 equals 2.00 seconds. And now we're going to say that instead of this object being dropped, hey, look who it is, folks. It's Benny. Benny is going to throw the object down with an initial velocity of 3 meters per second. Otherwise, we're still answering the same problem. We are going to take a look at what the displacement would be after 1 second and 2 seconds if instead of starting with an initial velocity of 0, we start with an initial velocity of 3 meters per second. And then we're going to compare the speed after 1 second and 2 seconds, and we can compare those speeds to the speeds of a dropped ball. So first, let's focus on the amount of displacement that the object has after 1 second and 2 seconds. And here we're using the same equation that we used the first time. y1 equals v naught t1 plus 1/2 gt1 squared, and y2 equals v naught t2 plus 1/2 gt2 squared. Now that the initial velocity is not 0, we cannot cancel out or eliminate that. So it's going to be 3 meters per second times 1 second. And per second times 2 seconds plus 1/2 9.80 meters per second squared times 1.00 seconds squared. And that's going to be plus 1/2 9.80 meters per second squared times 2.00 seconds squared. Alright, so you can see the difference is only that now we must account for an initial velocity, and in this case it's going to give us an initial position of 7.90 meters after 1 second, and for this one it's going to be 25.6 meters for 2 seconds. So comparing one to the other, we can see that with an initial velocity it will make it further down after each second. But now we're going to compare the velocities. Now velocity, part B, we can solve for the final velocity is going to equal the initial velocity plus acceleration due to gravity times time. So for velocity 1, it's going to be this, and for velocity 2, it's going to be g2. So now we can just plug in our values. 3 meters per second plus 9.80 meters per second squared times 1.0 seconds. And this one's going to be 3 meters per second plus 9.80 meters per second squared times 2 seconds. Alright, so we get, at T1 we get 12.8 meters per second, and at this one we get 22.6 meters per second. Now we can compare that when our initial velocity was 0 at time 1 and time 2. We get v equals v0 plus gt, but v0 is 0, so v1 and v2 would not take that initial velocity into account. So we could say gt1 and gt2, which if you plug in the variables for that, we get 9.80 meters per second and 19.6 meters per second. Now here we can take a look at comparing these two values. And it's actually really easy to do because the difference between these two is 9.80 meters per second, and the time interval there was 1 second. And hey, what do you know? Acceleration equals delta v over delta t. So that means that that's 9.80 meters per second squared. And up here we can do the same. Alright, we can compare the difference between these two values is 9.80 meters per second. That's our delta v. And our delta t between these two is 1 second, so acceleration equals delta v over delta t equals 9.80 meters per second squared. So we could see that while the velocity after each second for the thrown object is higher than the velocity of the dropped object, it's accelerating at the exact same rate in both situations. And you could do that for as many time points as you wanted, and that consistent relationship would continue to exist.